Causal discovery algorithms.
Thanks, Bob. So the talk is mostly about causality and the application of some ideas about causality from the machine learning community to quantum mechanics. So I'm going to start with just a couple of words. A couple of words about the traditional notion of causality. Okay, for some reason. What can we use that on? All right. So Hume was one of the people who first thought about causality deeply. And if you read Hume, you'll find this sort of quote which summarizes his views on causality. We call to mind the constant conjunction of things like the flame and the heat. In all past instances, and without any further ceremony, we call the one cause and the other effect. So effectively, Hume was saying that there's nothing more to cause and effect than constant conjunction. But this is not enough. There are many things that are constantly conjoined and correlated, which we would not say are imply a causal relation. So the rooster crowing doesn't cause the sun to rise, even though there may be a constant conjunction of those two things. So we're all familiar with the slogan, correlation does not imply causation. So the question is, what is it about the conjunction between the rooster crowing and the sun rising, that relationship, which makes us think that it's the sun rising that causes the rooster to crow and not vice versa? Well, if you cause the sun to rise at a different time, so for example, move the crow to a different time zone where the sun rises an hour earlier, then we expect that the rooster will crow when the sun rises. But if we make the rooster crow in the middle of the night by squeezing it or whatever, then we don't expect the sun to rise. So the idea is that causal relations support inferences about the consequences of interventions. So if you change something and A causes B, you go and you change A, then you expect to see some effect on B, whereas if you intervened on B, you don't expect to see some change on A, if A is the cause of B. So that's really the difference between causal relations and correlations. Causal relations may imply correlations, but correlation does not necessarily imply causation. So the questions that one naturally addresses, one naturally comes up with here is, do we have a formalism for describing causal relations? We have this really nice mathematical formalism for describing correlations. It's probability theory. Do we have a mathematical formalism for describing causal relations? What should it look like? And how do we come to have knowledge of causal structure? So by we here, I mean all of us. We do it as children. We learn to figure out what the cause-effect relationships in the world around us are. But scientists also figure out cause-effect relations in more subtle scenarios. And in the machine learning community, they are interested in designing systems that automatically uncover cause-effect relations. So the question is, how do you do that? So most of what I'm going to be telling you about is drawn from work on causality, which is summarized in these two books. So one's by Judea Pearl, and the other is by Spekkens, Gleamore, and Shane. And I recommend both of them, but particularly the epilogue of Pearl's book is quite nice. It's just a very informal introduction to all these ideas. And most of what I know about this subject comes from reading those books. So these are the guys who are working within the machine learning community and have developed a lot of the techniques for discovering causal relations. Causal discovery algorithms, they're sometimes called. So I want to apply those ideas to Bell's theorem. And so let me tell you what I think is the mystery of Bell's theorem, or what's surprising about Bell's theorem. So I think that the surprise is a certain tension that exists. So on the one hand, we have Bell inequality violations. And that suggests that if we want a causal explanation of the correlations you see in the experiment, then those causes have to propagate superluminally. So notice that I'm describing this not in terms of realism, but in terms of causation. Anyhow, that's how I'm going to summarize the consequence of the Bell inequality violations. And on the other hand, we don't have any possibility for signaling. So if there are these superluminal causes, then we can't use them. So they're there, and yet we can't make use of them in signals. And that seems sort of odd, that there should be something that's there, and yet you can't use it. So what I want to do here is clarify the sense in which there is a tension between these two things. So that's going to be one of the upshots of this analysis, is a clarification of that. And then secondly, by doing the analysis, it's going to show that there are some serious inadequacies in the algorithms that people have suggested for uncovering causal structure. And so those will be the two main points that come out of this. Okay, so let's start with mathematical formalism for describing causal structure. So causal connection, by which I mean being a cause of. So I'll introduce an ordering relation which describes causal connection. So the ordering relation is A is a cause of B. And by that I don't mean necessarily a direct cause, it could be an indirect cause. So what properties does this ordering relation have? It's transitive. So if you say that A is a cause of B and B is a cause of C, then A should be a cause of C. It's irreflexive. A cannot be a cause of itself. And it's antisymmetric. So if A is a cause of B, then B cannot be a cause of A. A causal structure I'll define to be a set of variables and a set of ordered pairs of those variables, specifying that X is a direct cause of Y relative to V. So here I'm interested in the direct causes. And it's relative to V because if I'm describing a situation, then the degree of precision with which I describe it may influence what the direct causes are. So, striking the match is the direct cause of the match lighting if I have a very coarse-grained description. But if I maybe go a bit deeper and I talk about the chemistry, then striking the match is just the direct cause of something else, which in a chain ultimately leads to the match catching fire. So it's a set of ordered pairs, which describes the causal structure. And you can represent any such thing by a directed acyclic graph, or a DAG. So the vertices on the graph represent variables, particular variables. And having a directed edge from one vertex to another represents that this variable is a direct cause of that one. So this will respect all the properties I've laid down. So it's acyclic, so there are no cycles. So that ensures that you can have transitivity and irreflexivity. Because these are directed edges, you have your antisymmetry. And so this is a very nice graphical way of representing a causal structure. Incidentally, I should have said, please interrupt me at any point with questions. Okay, so a causal model is basically going to be a causal structure together with extra stuff. The causal structure is sort of a skeleton of what causes what. A causal model is going to tell you something about the causal strength of different connections. So it's going to be a causal structure and a set of parameters. And those parameters describe conditional probabilities of this form. So the probability for some variable taking a particular value, given the parents of that variable taking certain values. So, for example, I should specify what the probability for the different values of B are, given the different values of its parent, and in this particular DAG, it only has one parent, which is lambda. So parent is just something which is a direct cause of that variable. So I'm going to use the terminology of kinship in these DAG scenarios. So parents are the causes. I think descendants are things in the tree that spawns out of a particular node.
Why wouldn't little b also be a parent?
Sorry?
Why wouldn't little b also be a parent?
Oh, you're right, little b. Yes, little b is also a parent. That was a test to make sure you're paying attention. Very good. You get a cookie. Good. So if I want to supplement this causal structure into a causal model, I need to specify things like this. The probability of A given its parents. So it turns out here A has all four of these guys as parents, so I need to specify this. If I look at capital B, it has B and the lambda And the rest of them have no parents, so this is basically telling me to specify the probability distribution over those variables given nothing. So just specify the probability distribution. Now I should say that you can think of these probabilities in various different ways. So, for instance, you might say, well, we're describing a world where there's objective stochasticity, and this is just, the chance of B taking a particular value given certain values here. But it could also be that really what's going on is that there's a deterministic connection between lambda, little b, and some other hidden variables that we're not taking into account, and capital B. So I could always draw another node and another variable, and I could say the value of this guy depends deterministically on these other variables. But if I ignore this one, then I just get this probabilistic dependence. So sometimes people write down what are called functional causal models, where they draw a bigger graph that has all these latent variables in it. They write down deterministic functions for every variable given its parents in that larger graph, and then you can compute these probabilities from that.
Sorry, how many probabilities are there? Are there 5? Are there or 9? I'm not quite sure what your notation is.
These are 5 conditional probabilities. So this is a function from the Cartesian product of these sample spaces to the reals between 0 and 1. So for every pair of values on the right of the conditional, I have a probability distribution for the sample space of that guy. So yeah, for this talk, I'm just going to specify these conditional probabilities as a description of the causal model rather than these deterministic functions. And now note that these exogenous variables, which is just a fancy way of saying the ones that have no parents, like these guys here, they are assumed to be independently distributed, so I don't have any correlations between lambda, little a, and little b. And if I look at the joint, it's just the product of these guys. And the reason for that is that the spirit of these sorts of models is to not allow for any correlations that aren't explained causally within the model. So you don't want a situation where you assume these guys are correlated, but there's no explanation of it within the causal model. So if indeed these guys are correlated, then you want to add in some other variable, which is a common cause, or you want to add a direct cause from one to the other to explain that correlation. So let me just say a little bit more about that. So there's this principle due to Reichenbach called the common cause principle, which says that all correlations should be explained by some causal relation. So if you see two variables that are correlated, then you conclude that either A causes B, B causes A, or they have some common cause. And that idea is built into these causal discovery algorithms, that it's appropriate to always look for causal explanation of any correlations. And I would say that science is really about doing justice to that principle. Typically, if we see correlations, as scientists we say, right, let's figure out the causal explanation of why that correlation is there. And so the particular way in which it's built in here is that all the exogenous variables have to be independently distributed. Okay, so now suppose I give you a causal model and you want to know what correlations can exist between the variables in that causal model. Well, the answer is very simple. You just take the probability of the exogenous variables times the probabilities of the other variables given what they depend on, multiply them together and you get the joint probability. That's it. Those are the kinds of probability distributions that can be supported by this kind of causal model. Right? So if, for example, I did an experiment where I sampled lambda A and B from these distributions, and then I sampled capital B from this conditional distribution, given what I got for these guys and so on, and I generated a set of data of all 5 of these guys. And I did this many, many times, and I said, what's the probability distribution over the data I've generated? It'll be precisely this one that I've written down. So causal models basically entail correlations. And what we're going to want to do is try to figure out how to go the other way. So let me tell you something about features of this, this probability distribution that are implied by the causal model. So to do that, I need to introduce the notion of conditional independence. So conditional independence, so we say two variables, A and B, are conditionally independent given C if any of the following equivalent conditions hold. So the first condition is that the probability of A given B and C is the same as the probability of A given C. And basically that just says, okay, if you already know C and you want to learn about A, then compare the situation where you don't learn B to the situation where you do learn B. And the answer is you don't learn anything more about A in the context of already knowing C by learning B as by not learning B. So in the context of already knowing C, learning B doesn't teach you anything about A. That's what conditional independence means. Another way of saying it is that C screens off any correlations between A and B. So there might be correlations between A and B, but they're always mediated through C. Here are two other equivalent ways of writing it. So the probability of B given A and C should just be the probability of B given C. So again, correlations between A and B are mediated through C. And then the third, which maybe is the most familiar way, is that if you look at the joint probability of A and B given C, it factorizes into the probability of A given C and the probability of B given C. And so these, the equivalence between these three just follows from the definition of conditional probability. It's very simple to prove. And here I'm just going to denote it this way. A is conditionally independent of B given C. Good. And so now there's a very simple theorem you can prove about causal models, which is that if you have a distribution that's induced by a causal model, then every variable x in that causal model is found to be conditionally independent of its non-descendants given its parents. So remember the kinship notion. Non-descendants are things that are outside kind of the tree that comes out of a node, and the parents are just the direct causes of a node. So let's consider an example. So x1 is independent of x2 given the parents of x1, but x1 has no parents. So given nothing, x1 is independent of x2. That's one of the consequences of the theorem. And that makes sense, because in the causal model, these are exogenous, therefore they should be independently distributed. Here's another example. x2 is independent of x1 and x4. So x1 and x4 are both non-descendants of x2. x2 has descendants x3 and x5, so x1 and x4 are part of the non-descendants. So this is another instance of the consequence of the theorem. Here's a slightly more complicated one. x3 is conditionally independent of x4 given x1 and x2. So if I look at x3, I ask what are the non-descendants of x3? Well, x5 is the descendant, x1 and x2 are its parents, so x4 is a non-descendant of x3. If I wanted to be more precise, I would say the non-descendants excluding the parents, which just would have taken more space. But x3 should be conditionally independent of x4, its non-descendant, given its parents, which are x1 and x2, and so on. So you can deduce all these conditional independence relationships from this theorem. And then furthermore, there are others besides these that you can deduce. So for example, x4 is conditionally independent of x2 given x1. So you could look at the probability distribution, calculate the conditional probabilities of x4 given x1 and x2, calculate the conditional probability of x4 given x1, and see that they're the same. But a simpler way of doing it is just to realize that there's actually some structure to the conditional independence relations, and you can derive all the conditional independences from a generating set using a certain set of axioms. Okay, so these axioms follow from classical probability theory. They're called the semi-graphoid axioms. And I mean, you can prove them, but they're very intuitive. So take the first one, for example. It says that if U is conditionally independent of W given X, then W is conditionally independent of U given X. So what does it mean? If you already know X, and learning W teaches you nothing about U, then in the context of already knowing X, learning U teaches you nothing about W. Or take a look at this one. If in the context of already knowing X, learning W and Y teaches you nothing about U, well then learning W alone teaches you nothing about U. Because if W and Y tells you nothing, well then clearly learning less will tell you nothing. And similarly, you can talk through these ones as well. And from this set, you can get all the conditional independence relations that exist in the probability distribution. Questions? Okay, so then the project here is to ask whether we can go the other way. So far, I've derived facts about correlations from the causal structure, and we want to know whether we can go from features of the correlations to a causal structure that explains those correlations. So the answer is that you can under certain assumptions. So you have to make certain assumptions which are plausible, and then you can get some information about the causal structure from the correlations. So let me sort of give you a warm-up version of this. So here's the question. Suppose you've got 3 variables. They're all bit-valued variables. So A, B, and C only take 2 values each. And then I tell you the following facts about the joint probability distribution over A, B, and C. A and B are marginally independent. So if I take just the marginal on A, B, the probability of A and B, I find it factorizes into the probability of A times the probability of B. But when I look at the marginals on A and C, it doesn't factorize. A and C are marginally dependent, and B and C are marginally dependent. So the question is, what is the natural way of explaining this causally? C causes both A and B. So if C were to cause both A and B, then you can imagine
they would be correlated.
They could be correlated.
A and B equals C.
Yes, A and B separately cause C, because if A and B are exogenous nodes, then they're going to be independent. But because they jointly cause C, then there's a mechanism for A and C being independent and B and C being independent. So for example, C might be the logical AND of A and B. Then that would satisfy these relationships. So that's the natural explanation, but you can imagine another one. You could say, oh, it could be this. B causes A, and C is a common cause of A and B. It could be that, but to explain the independence of A and B under this causal model, you have to presume that the correlation that's set up by this causal path and the correlation that's set up by this causal mechanism precisely cancel one another. And you can do that. You can set up examples wherein maybe this causes them to become correlated, this causes them to become anti-correlated by precisely the same amount, such that when you take the average, there's no correlation. And I'm going to flash an example, although it's not particularly instructive. So if I take this probability distribution over A, B, and C, so the notation here means probability corner that A, B, and C take value 0, 0, 0, probability corner that they take value 0, 1, 0, and so on. And notice that here C comes out as the AND of A and B, because it's 1 when A and B are 1, and 0 when A and B are anything else. And you can calculate what the marginals look like. And it turns out you can generate that probability distribution by the sort of intuitive model, which is that A and B are both coin flips, and C is just the AND of A and B. So the probability of C given A and B is, well, if the probability for C equal to 0 is 1 if A and B is 0, and the probability for C being 1 is 1 if the AND of A and B is 1. And so that can explain this, but I can also explain it with this other causal structure in a much more intricate way. So it so happens that if you take the distribution over C to be this, and the conditionals for B given C equals 0 and C equals 1 to be these things, and the conditionals for A given BC to be these precise things, and you work it all out, you'll find that you can reproduce exactly the marginals that you need to reproduce. You can get A and B independent, and everything's fine. So that's sort of bad news for causal discovery, because it says, well, look, there's lots of ways you could explain those correlations. But here's where the key assumption comes in. It's called stability, typically, and what it says is that the probability distribution is defined by a causal model is called stable if the conditional independencies in that probability distribution still hold for any variations of the parameters in the causal model. So if I change slightly the conditional probability that describes the causal connection between one node and another, I shouldn't suddenly lose conditional independence. And that's exactly what was going wrong that's exactly what would happen in this model over here. If I change these probabilities slightly, then I won't have A and B being independent. So basically, this causal model needs to be fine-tuned to explain the conditional independences we see. And the assumption of stability is that you should not posit a causal model that requires fine-tuning to explain your data. That's just bad form. You know, it's implausible that the causal structure is fine-tuned. So
such a system could exist.
Such a system could exist.
And such an algorithm would be unable to.
Such an algorithm wouldn't find it, right? So it's kind of an Occam's razor sort of approach that we're going to assume that we're not in this very special situation where nature is deceiving us into thinking the causal structure is one thing when in fact it's something else. And I think it was Pearl's book, or no, maybe it's Gleamer's book, they use this example that, you know, when you look and you see a chair, well, it's possible that there's another chair behind it and it's aligned just so that you can't see it. And so it's consistent with the hypothesis that there are really two chairs there. But, you know, we tend to assume that there's just the one chair because that's the most natural assumption. And stability is a bit like that.
There's some connection with minimality, that like a stable thing is always minimal or something like that?
Minimal in what sense?
Less causal relationships. Sort of the extra causal relationships like singularity.
There is a kind of assumption of minimality when you start introducing hidden variables. And I'm not going to get into that, but I mean, there is an assumption that they call minimality, and it has to do with sort of introducing, if there's some extra variables that are needed in the causal explanation, you want to introduce as few of those as possible. That's another kind of Occam's razor sort of principle. I'm not sure, maybe I could construct an example of something that failed to be stable but had fewer causal connections. Maybe not, maybe you're right. Maybe the things that are stable will have fewer causal connections than things that are unstable. But I would have to think about it.
For that sort of chair example, you could make more observations to quickly rule out that fine-tuned hypothesis. Is that somehow always the case realistically for anything that's sort of fine-tuned?
Yeah.
If you continue to collect data.
Well, if you had a handle on the parameters in the causal model, then you could try varying them and ask, well, which conditional independences are invariant under those variations. And in fact, you know, going back to my first slide, causation is really about intervention to some extent, right? That, you know, if I do one thing and I can influence something else, then there's a causal relationship there. So ideally, your experiments would involve interventions. You know, you do something, you see what happens. And the causal discovery algorithms I'm describing here are ones that have a much harder task because they're not basically allowed to use data of that form. Yes. So all they get is just, here's some correlations. That's it. You're not allowed to go in and do interventions. Maybe, you know, the correlations come from an experiment that's already been done and the system
But this assumption replaces that, in a sense. It allows them to assume that they would have been able to vary their parameters.
Yes. Well, I don't know if it replaces it. I mean, ideally, you would do the interventions and you would see what happens. But you know, sometimes you just can't do the intervention. So, you know, an example is that it might be unethical. So, you know, does smoking cause lung cancer? We'll come to that. Do you make a bunch of people smoke to find out what happens? Well, that's unethical. So you can't do the intervention that you'd like to do. So you kind of have to work around that and say, well, can we make some inferences about causal structure? Some plausible inferences without making interventions. So stability is really I think you should think of it as a plausible assumption. It may sometimes fail, but it's typically plausible. And you might be worried about assuming a causal model when stability fails because then you have to grant that that's sort of unnatural. You're saying, oh, the reason that I see these independencies is because everything's fine-tuned. I mean, that's sort of a delicate, I mean, in physics, the term fine-tuning is usually meant in a derogatory way, you know, that there's something wrong with your model if you need fine-tuning. Other questions? Okay, so let's get to this question of smoking and lung cancer. So this is meant to be sort of an example of how these causal discovery algorithms work. So Bob, pay attention.
It is.
So you see, so let's say you collect a bunch of data and you see a strong correlation between people who smoke and people who develop lung cancer. But you're not sure whether it's causal. And in fact, the tobacco companies, said that actually it's probably more likely a common cause. It's a genetic factor that causes people to want to smoke and predisposes them to getting lung cancer. And so they should keep selling cigarettes. So you want to try to resolve that kind of question. And now suppose that you go to the lab and you notice the following, that you observe a third variable, which is whether or not there's tar in the lungs of these individuals. So you got this data set, for every individual, either they're a smoker or not, tar in the lungs or not, and whether they developed cancer or not. And then you notice something about the full probability distribution. You find that S and C are conditionally independent given T. Okay, so if you calculate the conditional probability of having cancer given smoking and tar in the lungs, you find it's exactly the same as the probability of having cancer given tar in the lungs. Okay, so that whether they're a smoker or not becomes irrelevant once you've conditioned on tar in the lungs. Equivalently, when you look at the probability of cancer and smoking given tar in the lungs, it factorizes into the probability of smoking given tar in the lungs, which has the probability of cancer given tar in the lungs. So this is what you find in your data, and you want to say, okay, what can I infer about the causal structure from that? Okay, so here's how it works. Posit a particular ordering of these variables. So let me start with this ordering, S, T, and then C. I'll go through the other orderings in a moment. So here's a fact about probability theory. Any joint probability distribution over three variables can always be decomposed into the probability of one times the probability of another given the first times the probability of the third given the other two. Every distribution can be written in this form. And so I've chosen this particular, there's lots of forms that can be written in for other orderings. I could also write in a form where it starts with T and then S given T and so on. So I'll start with this ordering and just write in that form. And then I use the known conditional independence that we've observed. Oh, sorry. I can always now draw a causal structure that this form suggests, right? So if for example, S is the cause of C and the cause of T, and T is the cause of C, then the causal model that was defined by this would have exactly this form. S would be exogenous, and I would assign a probability distribution to it. T would depend only on its parent, which is S, so I would have some conditional probability. And C would depend on both T and S, so I'd have this conditional probability. So this is the kind of decomposition that would arise if this were the causal structure. So now I apply my conditional independence relation. S is independent of C given T. And that has a consequence, which is that the probability of C given T and S is just the probability of C given T. Because learning S in the context of already knowing T tells you nothing about C. And so I plug that into my my probability. I say, well, this term here doesn't have to be P of C given Ts. It can just be P of C given T. And what that means is that I could have done with it, I could have explained distributions of this form using a simpler causal structure, wherein the only cause of C is T. I don't need S causing C anymore. The only cause of C can be T, because a causal structure like that can generate distributions of this form. So that's a candidate causal structure that could explain the correlations you see in the conditional independence. Okay, let's look at a different ordering. Suppose you take C, then T, then S. You decompose it into, a prime over C, conditional. That's this causal structure here. You use conditional independence, and now you just find that you can drop this arrow from C to S. Again, this conditional independence allows the probability of S given CT to be just the probability of S given T, and so this causal structure suffices for generating correlations with that conditional independence. So that's another candidate for the causal structure. Say you take T, then S, then C. This is the decomposition you get, and the causal structure. You apply conditional independence, and it leads you to simplify the last term again, and you get something that looks like this. And then you sort of get the idea. I take another ordering, I simplify, and I actually get the same causal structure in this case. So in this guy, I was told, well, you can drop this arrow, and this causal diagram here had exactly the same structure, except this arrow is pointing the other way. So when I say, well, you can drop this arrow, I left with the same possible causal structure. So that happens sometimes, that you find that you don't get any new causal structure coming out at the end. Okay, what if you take an ordering like S, then C, then T? Things are a little bit different. There's the causal structure. But now if I look at my conditional independence relation, S independent of C given T, it can't simplify this expression at all. Because over here I have the probability of T given C and S. And this kind of conditional independence doesn't have any consequences here. Because this implies things like the probability of C given S and T simplifies. Or the probability of S given C and T can simplify. But it tells you nothing about the probability of T given other stuff. So it doesn't help you simplify this expression at all. So I'm just left with this causal structure. And similarly, if I started out with this ordering, C then S then T, I also get no simplification. So these causal structures are candidates, but they don't satisfy stability. So the only way I can explain the conditional independence we saw in the data using these causal structures is by assuming a fine-tuning of the parameters. So if we assume stability, then we have to rule these two options out. And so that's where these causal discovery algorithms start narrowing down the possibilities. So I found 3 causal structures that did satisfy stability. So for these 3 causal structures, even if you vary the parameters in the model, it's still the case that S and C are conditionally independent given T. You might recognize these as Markov chains. So Markov chains are defined to be chains of 3 elements where the 2 on the edge are conditionally independent given the 1 in the middle. So now you're down to these 3 possibilities. Now suppose you have one extra piece of data in addition to the conditional independence. Suppose you find that your patients always smoke before they have tar in the lungs. You never find tar in the lungs before somebody has smoked. So you realize, okay, the causal relation can't go from tar to smoking. So that rules this guy out, that rules that guy out, and this is the only one that's left. And so you say, all right, if these factors are all the causally relevant ones, then that must be the causal structure. Smoking must cause tar in the lungs, which causes cancer. Good. So, any objections to that?
Well, there were times where people sort of pour tar in somebody's mouth just for torture.
Yes. How have you ruled out the tobacco lobby's claim that it's due to a common gene?
Good. Good. So I haven't, and so there's 2 caveats to what I've said here. The first caveat is just that sometimes you might not have this temporal information, which allows us to exclude these guys. But secondly, all I've done here is to suppose that S, C, and T are the only things that are causally relevant. And I've just excluded the possibility, starting out, that there might be some other factor, like a genetic factor, which is causally relevant. And so, effectively, in another language, I've assumed that there's no hidden variables, which might be common causes in explaining these correlations. And so this isn't adequate as a response to the tobacco lobbyists. And indeed, people have introduced algorithms that suppose that there could be hidden variables, and those algorithms are a lot more complicated. But you can do similar things for trying to figure out how to explain the correlations given the possibility of some extra variables. And as we mentioned earlier, typically you want to minimize the number of extra variables you assume in your causal explanations. But I'm going to be using these algorithms for half the talk, and I'm not going to say much about the other algorithms. Good. Other questions?
Is it just a feature of this example, or is it a general feature that candidate causal structures only differ in directness?
Well, if you say, look, I have these observed variables, and I'm going to assume that they're the only causally relevant ones, then all you can have is, you don't have any other nodes, so your set of nodes is fixed, so all your graphes have the same set of nodes. You might find causal structures that have different numbers of arrows, right? So maybe you could say, well, here the only stable ones all have the same number of non-trivial links. I don't think that's a generic feature. I mean, you can find other more complicated examples where the number of causal connections might be different. And notice that there is an example if this skeleton is not on this list, which is the one where S causes T and C causes T. And it's not on this list because it doesn't explain the conditional independence of S of C given T. In fact, if S causes T and C causes T, then when I condition on T, I expect to see a correlation between S and C. Right? Like in my AND gate, if T is only 1 when they're both 1, and then I condition on T and I see 1, well now update my distribution for these guys to be correlating. Okay, so I want to talk about what these kinds of algorithms say about the Einstein-Podolsky-Rosen correlations and Bell correlations. So let me remind you of the relativistic notions of causality that are used in discussions of Bell's theorem. So, and I'm going to do it in the language of conditional independence. So the no signaling condition, which is that, so in this space-time diagram, time is up, space is on the horizontal. These are space-like separated regions. These are the backward light cones. That's why we know they're space-like separated. And little a and little b correspond to the measurement settings on the left and on the right. And big A and big B correspond to the outcomes you get from those measurements. And for simplicity, let's just assume they're all binary valued. So usually we say, okay, no signaling says that by changing the setting over here, I can't influence the outcome over there. But to be more precise, even if I know this setting over here, so Alice is sitting over here, she knows the setting. Even if she knows the setting, there's still no correlation between her outcomes and the choice of setting over on Bob's side. Right? So if Alice knows the setting at her side, then learning the setting at Bob's side will not lead her to update her probability distribution over the outcomes she might get. That's the content of no signaling. If it did, then you'd expect that Bob could change the setting here, change the distribution of her outcomes on Alice's side, and they could use that to signal. And then similarly, going the other way, the outcome on Bob's side should be independent of the setting on Alice's side, given the setting on Bob's side. So that's an operational notion. It doesn't refer to hidden variables at all. Bell's notion of local causality does refer to hidden variables. It says that we could imagine that there's some hidden variables. I think hidden variables is maybe not the best term. Let's just call them ontic variables, things that are real. They might include just the quantum state. They might include more. So orthodox quantum mechanics, where you think the only thing that's real is the quantum state, is included in this analysis. So if you have some hidden variables, then you can imagine that the correlations between the outcomes are due. These hidden variables might be a common cause for those outcomes. That's where the correlations might come from. But it still ought to be the case that if you condition, for example, on the setting on the left and the hidden variables, and you ask about the probabilities for the outcome on the left, they should be independent of anything that's going on in the space-like separated region. The idea is that by conditioning on these things, you've already got all the relevant information that's in the backward light cone of capital A. You've got the setting, and we assume that lambda basically includes all the stuff that's relevant for fixing capital A. And so when you've already conditioned on that, learning about things that are over here in the space-like separated region won't cause you to update your knowledge about capital A. That's Bell's notion of local causality. You can find it in, he has a 1970 paper, I think it's called A Theory of Local Variables, where he makes it explicitly this notion. And then you have to have it in the symmetric sense as well, that the outcomes at B, once you've conditioned on the setting at the right and the hidden variables don't depend on the setting or the outcome on the left. That's local causality. And then finally, there's some extra assumptions that typically go into derivations of Bell inequalities, which are that the settings are independent and the experimenters have the choice to make whatever setting they want. So in particular, those settings don't depend on the values of the hidden variables. And so the best way to represent that is that A, the setting on the left, is marginally independent from the setting on the right and the hidden variables. Right? So there's no correlation between the setting on the left and that. And not only is there no correlation between A and B, and between A and lambda, but there's no correlation between A and the pair B and lambda. So it could be that whenever these guys are similar in some way, well, that influences A. No, that's ruled out as well. So and vice versa for B and A lambda. So that's basically the assumption of free will and independence rolled into one. Okay. So let's consider these two kinds of correlations. How many people here are unfamiliar with this stuff? Or I should say, how many people are very familiar with this stuff? Most. Okay, well, I'll explain it because there were some hands that didn't go up. So say you start with this entangled state between two spin-half particles. So these are eigenstates of Z spin. And then you imagine separating the two parameters far away, and on the left-hand side, you either measure in the z basis or you measure in the x basis. So this is a plane of the block sphere, just to schematize that. And on the right-hand side, you also either measure in the z or you measure in the x. Okay? So there's four possible measurements that are done. Both z and x and z, or z and z, or x and x. And you look at the correlations that quantum mechanics predicts, and this is what you find. So I'm going to call a equal to little 0 the case where you've measured z, and little a equal to 1 the case where you've measured x, and capital A is the outcome you get. So what you find is that if on the right Bob measures z, and on the left Alice measures z, then the outcomes they get are perfectly correlated. That's what this predicts, right? If you measure z, you'll collapse the wave function and you'll get perfect correlations. So you get 100% correlation when you happen to do these two measurements. If you happen to do both x measurements, then you also get perfect correlation. But if Alice measures z and Bob measures x, then there's no correlation at all between their outcomes, because, for instance, if Alice gets up, then she collapses Bob's system to up along z, and then Bob measures x and he just gets random statistics. There's no correlation here, and there's no correlation here either when Alice measures x and Bob measures z. So those are the kinds of correlations that we see experimentally, and we want to know what that implies about the causal structure that might underlie those correlations. So now what about the Bell case? So Bell pointed out that Einstein was right in the sense that these kinds of correlations can be explained with appeal to local hidden variables. It's only if like Heisenberg and Bohr, you think the quantum state is a complete description of reality, that you have to assume that there's something non-local going on to explain these correlations. But Bell said, well, are there some other correlations in quantum mechanics which, even if you assume hidden variables, cannot be explained locally? And he found some. So here's the simple example of CHSH. Alice measures z or x. Bob measures along an axis that's between z and x, or an orthogonal axis. And if you look at the correlations in the results for this state, what you find is that so here, Bob's measurement is going to be called the 0 measurement if it's this one, and the 1 measurement if it's this one. And what you find is that if Bob does his 0 measurement and Alice does her 0 measurement, then they get correlation in their outcomes 85% of the time, roughly. And similarly, for these three possibilities, 85% correlation. And if they both measure their 1 measurement, then they get 85% anti-correlation between their outcomes. And this is what you can't explain locally. And to explain that, let me just draw a simple diagram. So the straight line will mean correlation. So let me take something that doesn't happen in quantum mechanics, explain why you can't get it locally. And that will help me to explain this. So say you've got this scenario wherein, so this is sort of an imagined world wherein Alice and Bob each have two possible measurements they can do with two outcomes each. And whenever they both do the first, they get perfect correlation, 100% of the time correlation. Similarly here, 100% correlation in here. And here they get 100% anti-correlation. And the question is, can they explain this with a local model? So what it means to explain with a local model is that Alice and Bob have to be prepared with answers to the questions that will be presented to them. If Alice gets to her station and starts flipping coins to decide how she's going to answer, well then she's certainly not going to be able to generate perfect correlations, because Bob's going to answer something. And if she's over here flipping coins, well some of the time she's going to answer correlated with Bob, but some of the time she's going to be anti-correlated. So they can't be flipping any coins. They have to have deterministic strategies. And then you can say, well, what kinds of strategies might they have decided on ahead of time to try to generate these correlations? Well, Alice's strategy is going to look something like this. If I get asked the first question, I'll answer 0. If I get asked the second question, I'll answer 1. Something like that. It just has to be a specification of everything she's going to answer for every possible question. So you can say, is there some choice of strategies, of things that Alice and Bob are ready to answer for each of these guys that will satisfy these correlations? And it's easy to prove a contradiction, right? So suppose Alice was ready to answer 0 here. Well then, to get perfect correlation across here, Bob has to be ready to answer 0 here. Similarly, to get perfect correlation, Bob has to be ready to answer 0 here all the time. So it could happen that Bob gets the second measurement, And if he's not prepared to always answer 0, when Alice is prepared to answer 0 for this guy, then they won't get perfect correlation. So he has to answer 0 here. Similarly, if now that we know that Bob has to answer 0 here, we know that Alice has to answer 0 here, and then we don't have anti-correlation. And no matter what set of 0s and 1s you lay down, you'll always fail to respect one of those relations. So you can't generate these kinds of correlations 100% of the time. And furthermore, you can only get it right, you can only win this game 75% of the time, right? So if one of these 4 pairs of measurement is chosen, and they're chosen uniformly at random, then at best, with a given local strategy, like this one, you can hope to win 3/4 of the time. So the fact that you can win 85% of the time in quantum mechanics cannot be explained by one of these local strategies. That's my quick version of Bell's theorem. Okay, so good. So these are the 2 correlations that we want to look at, and we want to figure out what it implies about causal structure. So the first type satisfies Bell's inequalities and does admit of one of these locally causal models, and the second type doesn't. So ideally, we'd like our causal algorithms to see the difference between them. So we start looking at independences, and here's what we find. So in this experiment, well, the settings are independent, but then we find something peculiar, actually, that if this is really the state, then the probability of getting a particular Z outcome, say getting the up outcome, its spinning up outcome, is actually independent of whether you chose to measure Z or X. Because the reduced density operator for the first guy is completely mixed. And so it assigns equal probability to up and down, regardless of whether you measure Z or X. So you actually find that you have independence on the choices of settings of the outcomes. So the outcomes are not just independent on the distance setting, but they're independent on the local setting. And so that's just a feature of the degeneracy in that state, and it's not, it's very fragile. Like as soon as I move those coefficients off from 1/2, I won't see that. So suppose we instead use a state like this one here, root p and root 1 minus k, the coefficients, p is not quite equal to half. Then we can calculate the conditional independences, and this is what we find. The settings are independent. The outcome on the left is independent of the setting on the right given the setting on the left. And similarly, the outcome on the right is independent of the setting on the left given the setting on the right. And that's it. Those are the only independences we find in the joint distribution over the 4 variables, little a, big B, for this state and these measurements. That's it. And so that's the input to these causal discovery algorithms. All they care about your probability distribution is the conditional independences. But here's the problem. If we do it for the Bell correlations, we find exactly the same set of conditional independences. So you should recognize these guys. What are they? The 2 last ones. Do they look familiar? If I go back, it's no signaling. It's that the outcome on the left shouldn't depend on the setting on the right given the setting on the left. That's just no signaling. So what this says is that if I look at the probability distributions induced by these measurements on this state, I just have independence of settings, no signaling from right to left, no signaling from left to right, and that's it.
Just a stupid question about notation. You usually write independence with per with 1 line, right? You have done that.
Oh, so I think sometimes the perp symbol has 2 lines in it, sometimes it has 1 line in it, but they mean the same here.
Ah, okay.
Yeah, they mean, sorry, it's just different fonts, I think, is all that is. So you find that the only conditional independences are the no signaling constraints and the independence of the settings. And so in particular, there's no way that the causal discovery algorithms can yield a different conclusion for the EPR correlations and for the Bell correlations. Because the input to those algorithms is precisely the same in both cases. It's just the set of conditional independence relations. Therefore, these causal discovery algorithms can't possibly do justice to Bell's theorem, because they can't distinguish correlations that satisfy Bell inequality from correlations that violate Bell inequality. Okay, but what if we just say, okay, we know that they're not going to do justice, but let's try just see what they come back with. So we try that, and there's two kinds of algorithms, as I said before. There's those that don't assume any hidden variables, which I've sort of described in detail, and those that do. So I'll start with the first type, and I just want to see what do they yield. Okay, so before I do that, first I'm going to tell you what that Bell's assumption of local causality would imply about causal structure. So this is I'm not starting from observed correlations and deducing consequences. Here I'm just going to ask the question, what could a locally causal theory look like? Bell's notion of local causality look like in this framework? Well, this was the assumption of local causality that I wrote down a few slides ago. And in particular, if you assume no hidden variables, then there's nothing here. There's no lambda to vary. So if you're Heisenberg born, you think that lambda is a complete, that the quantum state is a complete description, then there's no extra lambda that can be a causal factor. So these assumptions just reduce to this, that the outcome on the left should be independent of the setting and the outcome on the right, given the setting on the left. And that just says that things that are space-like separated don't influence the outcomes on the left once you've conditioned on the settings on the left. Because there's nothing else. There's no other hidden variable that you can condition on. In fact, the outcomes are genuinely indeterministic, but they certainly don't depend on space-like separated things. That's what locality would be in the context of no hidden variables. And then the independence of the settings and the assumption of free will, again, I just drop the lambda, and it just becomes the independence of the two settings. And so if I take all those independences, and I start with some particular order over my variables, and usually the settings come before the outcomes, so I'll choose an order where the settings are prior to the outcomes. Well, an arbitrary probability distribution can be factorized in this way, for this ordering, which is that kind of causal structure. I add in my conditional independence relations. Here they are. So A is independent of B. That means that this term here, probability of B given A, can be simplified to just the probability of B. This independence relation here, which is locality, tells me that this term, probability of A given B and A, can be simplified to the probability of the outcome A given the setting. And this final guy here can also simplify this one. So I do all those simplifications, and I get a causal structure that looks just like this. The outcome on the left can only depend on the setting on the left. The outcome on the right can only depend on the setting on the right. So that's the only causal structure that is locally causal if you have no hidden variables. Right? It's just, the settings can cause the outcomes, and that's it. So kind of obvious. So I could go through all the possible orderings as I did before, but you do that, and as long as you demand that the settings come before the outcomes, this is all you get at the end. Okay, so now what do these algorithms find for EPR or Bell correlations? Remember, they find the same thing for both kinds of correlations because they depend only on the conditional independence relations. So now we're just going to apply the algorithm. So we again start with this particular ordering. Here's what the decomposition of the probability distribution for that ordering looks like. That's the candidate causal structure. Apply the conditional independence relations, and you get simplifications. B does not depend on A here. This term here simplifies because the outcome on the left doesn't have to depend on the setting on the right. And this term here also simplifies because the outcome on the right depends only on the setting on the right, not on anything on the left. And so what you're left with is this kind of, what I said was wrong. This term here actually doesn't simplify because all we can really get from this relation is that the setting on the right, if I condition it on, the outcome on the right, conditioned on the setting on the left and the setting on the right, depends only on the setting on the right. That's all that comes out of no signaling. Right? No signaling, these are the things we've observed. They make no reference to any hidden variables. They're the only things we can put in to try to derive the causal structure. We're assuming that there are no hidden variables at all. And it turns out that this term here, in my candidate decomposition, doesn't simplify when I use this conditional independence relation. This conditional independence relation would have to be stronger. It would have to say that B is independent of little a and big A given little b. And that's not what no signaling says. That's not an instance of the no signaling constraint. So I can't simplify this term using no signaling. So it stays as it is. And that's the causal structure I get coming at the end. So capital B still depends on all the other variables. And if I go through all the possible orderings, this is the only two causal structures that are left over. So just the one I had and the symmetric version of it. That's what these algorithms would generate. That's sort of what's going on under the hood. But now notice that for these things to explain no signaling, you need fine-tuning. Because there's a mechanism for signaling, right? Like, there's a causal arrow here and there's a causal arrow here. And the only way I'm going to explain this independence relation is by saying that whatever correlations are set up this way are cancelled out by correlations set up this way. And so the only causal structures that are returned here are ones that fail the stability criterion. There aren't any causal structures that satisfy the stability criterion. And so if you just turn the crank, you find that the algorithm actually says, sorry, there are no stable causal structures. You know, fail. But the point here is that, well, here's the take-home message. If you deny that there are hidden variables, then EPR correlations are sufficient to infer superluminal causes. Einstein already showed that way back in 1927. He said, look, if you're unwilling to admit hidden variables and the quantum state is complete, you have to admit there's this null locality. So that's given. But what he could have added and didn't, and I think is interesting, is that to ensure that these superluminal causes can't be used for superluminal signaling requires fine-tuning. You would need to set up your causal relations in such a way that correlations that are induced by those causal relations to precisely cancel one another out, so that you really can't have any signaling. And that's something that's highly unnatural about any appeal, any attempt to have a causal explanation of these EPR correlations. Okay, so let me finish with the case of local causality. I'm basically out of time. If you ask, in the context of assuming hidden variables, what does locality imply? I won't go through the explanation. But you use Bell's notion of locality together with free will and independence, and you find this causal structure. And it's sort of natural. It says any correlation between A and B can be due to a common cause, the hidden variable, and also there are causes from the settings on the left and the settings on the right to the outcomes there. So that's the causal structure for any locally causal model. And now you say, well, what do these algorithms find given the observed independences in the correlations? So, drum roll. This is what the algorithms return. It's the thing that Bell's theorem says can't explain the correlations. So we knew that there was going to be a problem, right? Because both EPR and Bell give you the same conditional dependence relations. So the algorithms have to return the same answer for both. But one of them admits a locally causal explanation, and the other one doesn't. Because one satisfies the Bell inequalities, and the other violates it. So either the algorithm was going to be wrong in saying that there's not a local explanation for either, or it was going to be wrong by saying that there is a local explanation for both. And in fact, it's wrong in the second way. It says that there's a local explanation for both, when we know from Bell's theorem that there isn't. With this sort of small caveat that it actually admits for some extra freedom in hidden variables between the setting and the outcome. But that's not really relevant. So the punchline is that the algorithm claims that correlations that violate Bell inequalities can't be explained by a locally causal model, which means that these algorithms are not as clever as John Bell. Because John Bell realized that there's certain correlations that just can't be explained locally causally. And so there's a problem with the existing algorithms. Let me skip this and get to the conclusions. So the main conclusion is that if you want to assume superluminal causes, but no superluminal signaling in your attempt to explain what's going on with Bell correlations, you are denying a fundamental principle of our best current causal discovery algorithms, which is that conditional independencies that you see in your observed correlations should not require fine-tuning of the causal parameters. That's the only way you can relieve this tension between no superluminal signaling and superluminal causes, is to say, oh, everything's fine-tuned so that although there are superluminal causes, we just don't see them coming out in the correlations between observed outcomes. I should mention that if you want to try to escape the tension, or relieve the tension, you could say that, well, actually no signaling is just a contingent feature of our world, and maybe we're in a special equilibrium state, and it's not, maybe if we do enough experiments, we will find that actually we can signal faster than the speed of light. And that's how the tension is relieved, that there are superluminal causes, and we can use them to signal. And Anthony Valentini has a proposal quantum non-equilibrium that basically does exactly that. It says that we relieve the tension by assuming that we can signal. It would be nice to have better algorithms. So our current algorithms don't distinguish these things. They're not as clever as John Bell. And so there's an application here of ideas from quantum foundations to all the areas where we apply these sorts of things. And that's economics, medicine, social sciences. These algorithms are used in a lot of these fields. In foundations, there's a lot of sophistication about understanding what kinds of things can possibly be explained causally from years of thinking about Bell's theorem. And so we should bring that sophistication to bear on coming up with some better causal discovery algorithms that can actually do justice to the differences between correlations that satisfy and violate Bell inequalities. A couple of other things that I can say, work for the future. There's a lot of talk out there for a long time about maybe Bell correlations imply that there's some backward in time causation, and maybe that's how you can make sense of it. Well, because we didn't put time into these models, we could just take a set of correlations and extract out possible causal structures. We could start exploring these ideas, because we have a notion of causation that does not rely on a background time. And similarly, because we're defining cause in this way, you can allow for causal structure in the relativistic sense, space and time, to be emergent. So if I have a probabilistic theory, I could ask what causal structures are consistent with it. I could define what it is to be spatially separated as there's no causal connection, and what it means to be temporally related as there is a causal connection, rather than vice versa. So define space and times in terms of causal notions, rather than causal notions in terms of space and time. And then finally, I've been working with Matt Leifer and Bob and I have written a paper together on quantum analogs of conditional probabilities. And in those quantum analogs, you also have a quantum analog of the notion of conditional independence. And so you could, instead of taking a probability distribution and saying what causal structures are consistent with it, you could take a quantum state and say what causal structures are consistent with it, and try to explore Bell's theorem and other topics that way. So, thanks for your attention.
Are there any questions, comments? Yes.
I'm just trying to work out the hidden variables and what they can cause. Because you say you get a lambda being arrows to A and B.
Should I go back to local hidden variables, like this one here?
Yeah. No, anything
Nope.
like that. None of that. Was that one?
This one here. Okay.
I don't quite see what's wrong with that.
Okay, let me start by saying what's wrong with it, and then you can maybe ask again. So Bell said, look, the content of locality is contained in these kinds of statements. That, once you've conditioned on the setting on the left and the hidden variables, conditioning on things that are space-like separated from the left, stuff on the right, doesn't help you update your probabilities of the outcomes on the left. So outcomes on the left are conditionally independent of both the settings on the right and the outcomes on the right, given the settings on the left and the hidden variables. So Bell says that's the content of locality. And then you can just find that in this language of causal models, that implies that the causal structure has to be of this form. Well, that together with this idea that you have free will and your choice of settings doesn't depend on the hidden variables. Together with that, it implies that these are the only causal structures that are allowed. And that's intuitive. It says, okay, the correlations in your experiments are due to the common cause of some hidden variables. And that can certainly explain the EPR correlations. Bell showed that it can't explain the Bell correlations. And then you ask these algorithms, what do they say about causal explanations of EPR and Bell correlations? And the first thing you find is that it can't distinguish them. So you already know that something's gone terribly wrong. But you still ask nonetheless, well, what can you infer about the causal relations given the observed independence of the settings and no signaling, the observed independence of the settings on the left given the observed independence of the outcomes on the left given the settings on the right, given the settings on the left. There's no lambdas here, right? So Bell's notion of locality was different. It said, I can put a capital B in here and a lambda there. It says that nothing on the left depends on stuff on the right, given hidden variables in the settings. No signaling says something different. It just says the observed stuff doesn't depend on the settings, given the settings. So if you just plug this into the algorithms and you crank, you get the thing that Bell said could not explain these correlations. So we know that the algorithms have failed in this example. Now I haven't told you what's going on under the hood of this algorithm. All I did sort of earlier in the talk was say how the algorithms that don't assume hidden variables work. And that would be a longer explanation, so I haven't justified this to you, but you just have to take my word that this is what they return.
So
Yes?
kind of on that, can I just ask a clarification about, in terms of these algorithms, is it the case that what you plug into these algorithms are just these conditional independencies?
Yes.
Relations that you discover from the probability?
Yes.
You don't plug in the probability distribution and it works out the conditional independencies?
Exactly. You plug in the conditional independencies.
Right.
That's
So-
all it takes.
So it's not an algorithm that says, here's a joint probability system,
Right.
you plug it in,
Right.
and then it spits out the conditional independencies, the causal structure, and the hidden variable,
Exactly.
which is
So-
what would be a better system.
Yeah. So we know that if we wanted better causal discovery algorithms that can do justice to Bell's theorem, the nature of the inputs to those algorithms has to change. It can't simply be a list of conditional independencies. It has to include more information, something about the strength of those correlations. So maybe not the whole probability distribution, but certainly more than a list of conditional independencies. Yeah.
But given any actual realistic data,
Yeah.
you can never really get in such a clean way these conditional independencies. They'll always be approximate,
Yes.
right? And if you really want to apply these algorithms anyway in situations where you don't have much data,
Yes.
I wouldn't have thought, I mean, you can't even really extract this list anyway, so you want a more sophisticated set of algorithms where you can just give it all of the data and say, come back and give me a ranked set of...
Good point. There are other algorithms. So for example, there are algorithms that will return a probability distribution over candidate causal structures. So it'll say, well, this causal structure is highly likely to be the one because, this and that were very close to conditionally independent. And so that suggests that this is the right causal structure. But I think, so I haven't looked into those algorithms in detail, but my sense is that they still don't do justice to Bell's theorem. That I think all the concepts that go behind those algorithms are the same ones that go in here. That you want to ensure stability. In the hidden variable case, you sort of want to introduce minimal amounts of hidden variables to explain the independencies you see. So I don't think those algorithms, although you're right, those algorithms will take as input the whole probability distribution. They don't contain enough insight to really get the results we want here. So there's some ideas missing.
But those algorithms would completely fail for the Bell, in case of the Bell correlations, though. They would correctly say, I can find no possible model, right?
I don't know. That's a good question.
Because those models would not just be giving you back setups where you get the same conditional dependencies. They'd have to give you back setups which are consistent with the actual observed data, right? And in the limit of collecting arbitrary large amount of data, we know there is no possible local hidden variable model to obtain the Bell statistics. So I would expect those more sophisticated algorithms would have to fail. Maybe I misunderstand what these would be giving you.
I don't think I know enough about the details of those models to say for sure whether they would or wouldn't fail. I have to look into it.
Can I ask?
Yes.
Okay.
Yes.
I have a separate question. I don't want to hog the questions. Could you say a little bit more about the quantum analogues of conditional independence and so on, which you mentioned?
Right. Have you got an hour?
Well, I think maybe we'll go for coffee.
I can say something very briefly. So the key thing is that if you have a set of systems, say quantum systems, A, B, C, and let's assume that none of them are direct causes of any of the others. So there might be something that's a common cause of them, but they're acausally related relative to one another. So a standard example would be just, you've got 3 qubits and they're in some quantum state. So the quantum state over these guys is going to play the role of the probability distribution over the 3 possible variables. So the key thing is that Matt Leifer introduced a notion of a conditional quantum state. So if you have, say, a quantum state over two variables, and you want to define a conditional quantum state, you define rho A given B. So this is just going to be some operator on the tensor product of the Hilbert space of A and B. And it has the feature that it's positive, like a state. And if I trace over A, I get identity on B. And these are meant to be the analogs of the fact that a joint probability distribution would be positive, and if I marginalized over the thing on the left of the conditional, I would get 1 for everything on the right, every value of what's on the right of the conditional. So these are the analogs of what we would expect to hold for a classical probability distribution. So you have this notion of a conditional quantum state now, and then you can try the following. You can say, well, what if I try to define conditional independence of A and B given C as rho A given B C equal to rho A given C. And what this equation really means is that there's a tensor identity on B here. That things are trivial on the B space. We usually drop that in our notation. But you can calculate both these quantities. You know, here I have to, I haven't told you how to do it. Maybe, okay, that's the one other thing I'll say, that here's the definition of a conditional state. Classically, we have a way of calculating conditional probabilities from joint probabilities. It's just the definition of a conditional. And so quantumly, we have something analogous. A given B is determined by the joint by taking identity on A tensor rho B to the -1/2 on both sides. And for various reasons, this turns out to be a very good analog of this equation here. So I can calculate from this joint state, I can calculate this guy, I can take the marginal on AC and calculate this guy, and I can test this. And I can test other things like, is it the case that this guy is equal to rho B given C? And is it the case that rho AB given C decomposes rho A given C, rho B given C? So these are all the analogs of those three forms of conditional independence. And what you find is that they're almost all equivalent in the quantum context. So this implies this and vice versa. They both imply this guy. The only thing that fails is that from here you can't go back. You have to add an extra condition to go back. So you've almost got exactly the exact analog of the classical case. But you can use, say, these ones to define conditional independence and then start exploring that structure.
Yeah, if there are many more questions, we can go to the common room and have some cookies and coffee and tea and stuff. And we thank Rob again.